I welcome you all to this 7th lecture of the topology lecture series. So in the last lecture we had discussed what we mean by a basis for a topology. We had defined and gave examples of basis for a topology on a set X. We had looked at several examples. Today we will look into why we are interested in basis. So one of the foremost uses of a basis is they generate topology. Basis for a topology generate topology. There's a generic way of doing it. So we will discuss how, given a basis for a topology, can we generate topology. So let's get to that right away. Let B be a basis for a topology on a set X. So let me quickly recollect what are the properties that B has. B is basically a subset of power set of X, satisfying the condition that union of elements of B with the entire set, meaning for every X in X there exists a Bx in B such that X belongs to Bx. And it also satisfies, the collection also satisfies another property, that if a point X in X happens to be in the intersection of B1 and B2 from B, that is, if X is in B1 intersection B2, then there exists a B3 in B such that X is in B3, not only X but every element of B3 is an element of B1 intersection B2. These are the properties any collection which is a basis for topology satisfies or possesses. So once so we have a basis for a topology on the set X. So consider C to be collection of subsets U of X which satisfy the condition that for every X in U there exists a Bx in B such that X belongs to Bx and Bx is completely contained in U as a subset. So given a basis on a set X, let's consider collection of all those subsets U of X which satisfy this condition. That is, for every element of U we should be able to find an element of B, let me call it Bx, such that X belongs to Bx and every element of Bx is an element of U. This is basically some collection of subsets of X. Okay. first and foremost, this collection C is non-empty as X belongs to C, and that is because any element of B is basically a subset of X, and these conditions hold true immediately. And also X belongs to C because of this fact. Okay, so for any X in X, what we are sure about there a Bx such that X belongs to Bx. There exists a Bx in B such that X belongs to Bx. This we are sure, but why should this be a subset of X? Why? That follows from the definition, because any element of B is actually a subset of X. So this other half is kind of straightforward. That follows from the definition. So that's the reason this collection C is non-empty. In particular, it contains the entire set X. Okay. Our claim is C is a topology on the set X. So it should satisfy the axioms of being called a topology. That would require, that is, the trivial subsets of C. No, sorry, trivial subsets of X should be elements of C. That is empty set and X. We already demonstrated that X belongs to C. We just have to demonstrate that empty set belongs to C. Second requirement, C should be closed under taking arbitrary unions. We will be demonstrating this in some time. We will also be demonstrating that C should be or is closed under taking finite intersections. Okay, we will be demonstrating this. We have already demonstrated that X is an element of C. Let's see. Empty set belongs to C vacuously, holds vacuously. That's because if empty set were not to be an element of C, that would mean that empty set does not satisfy this condition that is laid out. So it has to satisfy the negation of this condition. That would mean implying that there exists an X naught in the empty set such that for every B in B such that X naught belongs to B and B is not a subset of empty set. I'm just writing the negation of this requirement for U equals empty set. All of this is not relevant to us because we encounter issues in the at this stage itself. So if empty set is not an element of C, would mean we being able to produce an element of empty set satisfying a particular condition. But this itself is impossible, being able to find an element of empty set. So this entire statement cannot ever be true. So this cannot be true. So that would basically mean that empty set has to belong to C. So whenever such arguments are made, they hold vacuously. The negation cannot be true. Okay, so that's the reason empty set has to be in C, and so we have demonstrated the first requirement. Now let's see why C should be closed under taking arbitrary unions. So let A be a subset of C, a non-empty subset of C, then we claim union of elements of A is an element of C. Now let point X. So basically what we are supposed to do, for every X in union of elements of A, we need to find an element, let's say Bx in B such that X happens to belong to Bx and Bx is contained in union of elements of A. Do this. Okay, so since X belongs to union of elements of A, would mean there exists a AX in A such that X belongs to AX. Okay, so X belongs to union of all elements of A. It means that there exists an element of A containing that particular X. Okay. So now since A is a subset of C, this would imply that AX actually belongs to C. And since X belongs to AX, there exists a BX in B such that X belongs to BX and BX is completely contained in AX. Okay, but what do we know? We know that AX is actually a subset of union of elements of A. That's because it is one of the elements taking part in the union. Okay, so this would mean X belongs to Bx and Bx is completely contained in union of elements of A. So this is basically what we wanted to demonstrate. So this implies that union of elements of A is an element of C. Okay, so finally to show that C is closed under taking finite intersections, we can it is enough to show that if A and B belongs to C, then A intersection B also belongs to C. It's enough to demonstrate this. And then by induction you can extend it for finitely many sets taking part in the intersection. Okay. So let A and B be elements of C, and X be an element of A intersection B. That would imply that X belongs to A and X also belongs to B. But then what do we know about A and B? Both are elements of C, and X happens to belong to each one of them. That would mean there exists a B1 in B such that X belongs to B1 and B1 is a subset of A, and there exists a B2 in B such that X belongs to B2, B2 is a subset of B. So this would mean that X belongs to both B1 as well as B2. And both B1 as well as B2 are actually elements of the basis B. Okay, and then the second property of a basis is that whenever you have a point in the intersection of two of its elements, there exists a third element satisfying these conditions. So there exists a B3 in B such that X belongs to B3. B3 is contained in B1 intersection B2, but B1 intersection B2 in turn is contained in A intersection B. That's because B1 is a subset of A, B2 is a subset of B, and B1 intersection B2 shall be a subset of A intersection B. So what we have, X belongs to B3, so there exists this B3 in B, okay, such that X belongs to B3 and B3 is completely contained in A intersection B. Hence A intersection B is an element of C. So whenever A and B are elements of C, we demonstrated that A intersection B is also an element of C, extending this by induction will yield that C is closed under taking finite intersections. Hence C is a topology on X. So what we had a basis on the set X, and then using the basis we defined a collection C of subsets of X satisfying a particular property. Then we saw that this collection happens to be a topology on C. This C is called the topology on X generated by the basis B on X. And C is usually denoted as by this symbol. So this is topology generated by basis B. Okay, so bases for topology are utilized to generate topologies. Now it's a small little observation that you can make, that elements of topology generated by a basis P are basically those subsets of X which can be written as union of elements, not all, some elements of the basis P. All those subsets of X which happens to be union of some elements of B happens to be elements of the topology generated by the basis P. Now clearly every basis is contained in the topology generated by that particular basis. That's because if B belongs to B, what are we supposed to do? For every X in B, we need to find a BX. Find BX in B such that X belongs to BX and BX is contained in B. And there's an obvious choice for B. You could choose BX to be B itself, and of course it would satisfy this condition. So every element of B is an element of the topology generated by the basis B. Okay, so elements of B are called basic open sets. Basic open sets of the topological space X with the topology generated by the basis B. Okay. So we had seen that on real line I, collection of all open intervals